Okay. So ductility, of course, for ductile materials such as gold, silver, and those materials are softer, and those materials are going to have larger ductility. And for brittle material, it's going to have a totally different scale on ductility. Start talk about brittle. So for brittle materials and metal experience little or no plastic deformation. For ductile material, the material is going to experience very large deformation, plastic deformation before fracture. And that's just a definition and kind of general knowledge about ductility, but we do have the equation to quantify what is ductility for different materials. We can use a math equation for ductility. And the symbol for ductility is, we have two different symbols. The first one is called %EL. That's a percent elongation. The percent elongation is kind of like this, how we define strain. It defines as the change of length, the final length minus the original length divided by the original length, and times 100. That will give you the percent elongation. This is the fracture length. And this is original length. That's one way to define what is ductility of a material, by measuring its length before the test and after the test when it breaks. Another way to measure ductility is by using percent reduction in area. We just mentioned that in Poisson's ratio, right? Percent reduction. For this case, we use percent, the symbol is percent RA, to represent that's a percent reduction in area. The definition is, mathematical definition is, the change of cross-sectional area. The original area minus AF, the fractional area, divided by AL times 100. AF here is cross-sectional. At the point of fracture. AO is original. Okay, so here are the two different ways to define what is ductility for a given material. And even for the same material, let's say for steel, and it could have different ductility at different temperature. So now we're starting talking about temperature. Temperature is very important thing for this course because all the material property are largely depends on the temperature. So in room temperature, most of metal material are moderate ductile. But if you lower the temperature, even a very ductile material can become very brittle. So if you have low temperatures, most of metals will become very brittle. Segment. All right. Okay, that's the first mechanical property, ductility. Another, can you think about any application for ductility? Why we want to define that as an important mechanical property for materials? Like stretching things in the wire. What? Like stretching things in the wire? Stretch things in a wire. Is that what? Yeah. Okay. And we're all engineers. If you design a product, do you want to use something that is brittle or do you want to use something that is more ductile? For example, we're designing a car. Brittle? You want it to be very brittle? Okay. If you think we should design using more ductile material, using brittle material, use our hand. Okay. So one application is we want to use something that is a little bit ductile in engineering design. Why is that? If there's extra additional stress applied to the parts, if you have a ductile material, what is happening? If something is ductile, it will experience large deformation before it breaks, right? A ductile material. It elongates longer until a point it breaks. So imagine what that would happen in a car. If you have a part under external stress and that part is deformed, become longer, then when you're driving, you probably hear the metal rattle noise of the car starting to vibrate. That tells you, okay, there's something wrong on that car, and you want to stop it and send your car to shop to get it checked, right? Imagine what is happening if you have a brittle material in your car. If there's a stress, your car hit a pothole, boom, a brittle material, it will just break without any deformation. It could be very dangerous. You don't know what's going on. Just suddenly your car could be if that is a very important component, then suddenly you're out of control on the road. You don't have that warning before it breaks. So for most of the engineering products, we want some type of ductile materials to be there to give us a little bit warning, which would tell us, okay, it's time to get it checked, fixed, or repaired. That's kind of, we talk about failure in chapter 8, and I'm going to mention more about that. The next mechanical property we're going to talk about is resilience. The resilience it's a capacity of a material to absorb energy where it deforms elastically, and then upon unload to have those energy recovered. Yeah, the definition is a little bit long. It's a capacity of a material to absorb energy when it is deformed, when it has elastic deformation. So here the keyword is elastically deformation. And then if you unload that stress to have that all the energy recovered. It's kind of like how much energy can store in a spring, right? All the elastic stream energy. And this resilience actually is related to our stress strain curve. It can be found, can be calculated from the stress strain curve. So the symbol for resilience, the modulus of resilience, that's introduce UR, that is modulus of resilience. That can be found from the stress strain curve. Remember stress strain curve? The definition of modulus of resilience is you integrate the strain curve all the way until the yielding strain. Well, I don't know, you don't like look at equations. Integration, okay. That's a headache, but there's an easy way to do this. If you have a stress strain curve, just find out where's the linear region, find out where's that yielding stress. Then you build a triangle, since the curve before that yielding stress should be a straight curve. The right triangle here will tell you information about resilience. The area of that red triangle equals the modulus of resilience. How to find area of a triangle? You find the length of the base times height, which is sigma y, divided by 2. You get the area. That one. So the area is sigma y times epsilon y divided by 2. And that equals your resilience, modulus of resilience. That's an easier way to do it. So if in the exam, I've showed you, I give you the stress strain curve of material, then they tell you, find what is modulus of resilience. Now you know, you don't have to do integration. And simply just finding the area under the curve.
Is that 2 or Z?
2, yeah, number 2. That's how you find area of a triangle. Okay. 2 minutes left. Okay. This is one equation to calculate what is modulus of resilience. Or if you want to have some fancy equations, you can also use another equation by plugging Hooke's law into it. And you end up with, you replace epsilon with Hooke's law, which is sigma divided by E. Then you can find resilience by using the yielding stress divided by 2 times E, which is Young's modulus. So yielding stress power divided by 2 times E. That also tells you resilience. But keep that in mind, no matter which equation you use, resilience only, it's a property just inside of linear region of your stress strain curve. For most of cases in this class. If you want to use this equation, it has to be inside of linear region. If a material doesn't have a linear region, then, like for example, doesn't have a linear region, then you have to use the first method, kind of find where's the yielding point, then find the area under that curve. Where's that y? Okay, that's all for today. We just have very little left for chapter 6. All right, we have homework. Now we have office hour from 1 to 2 today. If you have any questions, feel free to hop on my Zoom office hour. Otherwise, have a good weekend.